Recording. I need to kind of present chapter 8, sure. Okay, 8.2, 8.3, 8.4. This is Introduction to Wave Theory. These are the learning goals. We want to define a wave and all of these components of the wave relevant to its motion. We're determining the wave equation, analyzing the speed and frequency of wave, comparing and contrasting sound versus light waves. Um, in the grade 12, you will work more on light waves. The light can be treated as a wave or particle. You will see that in grade 12. Discuss factors affecting the speed of wave. Now, what is the wave? So you have seen the water waves, right? When you're disturbing the surface of the water, you produce some ripples. So it's defining as a disturbance traveling from one medium to another medium. So can you think of any waves you learned in the past? So you want to say that there could be sound waves, the waves that you create in a row, and so on. Now look at these components of the wave. So the wave, as you see, is kind of repeating things. You have done functions. You have seen the sinusoidal waves, sinusoidal functions, right? It looks like that. So a wave have amplitude. Amplitude means the distance from maximum to the equilibrium line or to the midline. As you see, the wave has a maximum, we call it crest, and it has a minimum, we call it throw. The distance between two equivalence points, we call wavelength. So maximum to maximum is the same point, right? The distance between these two same point gonna be wavelength, or distance between minimum and next minimum, right? Is not shown here. But if I continue this, and this is my minimum, the distance from minimum to minimum gonna be wavelength. Or the distance from here on equilibrium, which is going up, down, and then up. These 2 points that I just shows here, they are the same point. How do I know they are the same point? At this point, the particle will move up, and here is move up, right? That's why the behavior of the particle going to be the same. Can I say that these 2 points are the same as this point? No. The reason is that if you follow this path, the particle here go up, here the particle go down, so here the particle go down, right? So this point and this point, I know they have the same level, but particle here is moving down, so they are not going to be the same point, right? This point and this one, the particle is moving up. I hope it's clear what I mean by equivalence point. So the distance between any two equivalence points will be the wavelength. So again, I want to read this. Crest is the highest point on a wave, and a throw is the low point. Cycle or wavelength, we call it with lambda. So this is the symbol of that, a complete repetition of a sequence. So it's the complete cycle. And the unit of that is meter. Okay. And the time, we call it period. Period is the time for complete cycle. When you have a wave, the wave is moving forward, right? So if the energy is here and it's trying to move forward, so the time that it takes the energy to come from here to here is the time of one complete cycle. It will be period. And the unit for the period is second. Unit second. We call it period. Sometimes we call it a T, and some textbook they call it to say this is T. The symbol is T, big T. Can say that this is a time, right? Or some textbooks using the P. I believe I'm gonna go with T. Oh, the T is much more better, right? Also, we know the frequency. Frequency is F. Frequency, it's the unit for the frequency is 1/2 or hertz. It's number of cycle per second. How many cycle do you get per second? Like you wait 1 second and you say that how many wavelength it's moving forward. And I know second and 1/2, they are, you can see that there is a relationship between frequency and period. Frequency is 1/period. It makes sense. This is 1/2 and this side is 1/2. Okay, we'll repeat that concept more. Okay, so let's just move on. Time it takes to complete one cycle in a second. Again, frequency is number of cycles in a given period of time. Amplitude, I said, is maximum disturbance of a wave from its 0 point. So it's from the highest point to the equilibrium point, or the 0 point. So now here is the wave equation. I'm going to explain that. This is really neat. So wave, the velocity of the wave is wavelength over period. But really, that makes sense? Don't need to memorize that. Just need to understand where does that come from. So if you look at the wave, this is the one complete cycle, right? This is the one wavelength. From here to here, we have lambda. The distance that the wave travels in one complete cycle is lambda. You know velocity is going to be displacement over time, right? The distance of the one cycle going to be lambda, and the time of the one cycle, we define it as period. Okay, so easily the velocity can show that the velocity is lambda over period. And you know the unit for d lambda, which is wavelength, is meter, and the unit for period is second. So meter per second. It's really makes sense, right? Now, if you rearrange it, oh, instead of 1/t, we just said that frequency is 1/period, right? So instead of 1/t here, this is lambda 1/t. Instead of the 1/t, I can put frequency. So it's going to be frequency lambda. And that equation is universal wave equation. Okay? Universal wave equation. Okay, so well, let me just talk about this one. So we said the frequency is number of cycle per second, right? Then we can state that t, the period, is number of cycle per frequency. This is something that we could say, actually. I'm going to just put it here. Frequency, it's number of cycle per second. See, number of cycle per second. Then T um, instead of frequency, actually, instead of 1/2, I can put T, right? Let's just look at this. I'm gonna just adjust this one, 50 is equal to 1 over frequency. And instead of, so here, number of cycle is going to be frequency multiplied by second, right? Actually, this doesn't, I don't like it. Okay, let's just not go over there. I'm going to write it differently. So it would be second per number of cycle. Okay, just switch that around. So let's say that objects complete 25 complete cycles of something in a period of 5 seconds. How frequent is this motion? So since the frequency is number of cycle per time, what would you do? Frequency gonna be number of cycles, means 25 cycle per what? Per 5 second. If you do it, it would be what? Gonna be 5 cycle per second, right? So that would be frequency. And we call it 5 hertz. Is another unit for 1 over second. Now, to double the frequency, what can you do for this motion above? Okay, what motion above? I don't see it. Okay, for double the frequency, if you want to double the frequency, what do you do? I just want to go here. If anyone can tell me about that, if you want to double the frequency here, what would you change? Any volunteering to turn on the mic? Okay, to double the frequency, you have to double the numerator. So it's going to be 50 cycle per second, per 5 seconds. Or you need to have the time, like 25 cycle per 2.5 second, right? To make this one double. Okay, so example 1, let's just do this one. Calculate the period and frequency of a tuning fork whose vibrate back and forth 375 times in 3 seconds. So tuning fork, I want to find frequency again, number of cycle per time. So you have 375 cycle times per 3, right? 3 seconds. You want to do that. Direct 25, 1 over a second. If you want to find period, you do, it's going to be 1 over frequency. You got your frequency, right? 125. And that would be second. Okay? Any question? Second example, calculate the speed of the sound wave leaving the tuning fork. In the first example, the wavelength of one cycle is given to be 275. So I know the wavelength is 275. I know the frequency from the top. We got 125 hertz. I want to find the velocity. You need to use the universal wave equation, which is F lambda. Going to be 2 multiplied by 275. 550 meter per second. Any question? Okay, we have type of wave. We have two types of wave. We have transverse waves, longitudinal waves. Transverse is when the direction of the travel of the wave is perpendicular to the motion of the source. Okay, so what is this really? Let's say you have a rope and you put a disturb on it. So the molecule of the rope going up and down, right? See, this molecules go up, the next one go up, goes up, and here is a stop and then go down. So here is go up, and they go down, 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 they get to the minimum, and then go up, right? This molecule will not kind of move forward. They just vibrating up and down, but the wave or the energy move forward. The energy move forward, the molecule go up and down. That's why the molecules go up and down. It means the direction of the travel of the wave perpendicular to the motion of the source, the motion of the particles. Okay? Any questions? So they are perpendicular. Particle move up and down, then the energy move forward. Longitudinal waves, when the direction of travel waves is parallel to the motion of source. An example gonna be this springs, right? If you look at this spring, it would be compressed, right? And stretched. At some point, it's very compressed, and here is stretched. So at the position that they are very close to each other, kind of we have a maximum energy, and at a position that are very stretched, we have a minimum. You know the particle here moving back and forth, vibrating back and forth, and energy is moving forward, right? Energy moving forward, and the particle moving back and forth. As you see, the direction of the energy and the particle are along with each other or parallel. So these are the longitudinal way. And it's an example gonna be a spring when you just apply pressure at one end, so they vibrate back and forth. Or it could be wave sound. When you just try to speak, right? This is your mouse. You try to speak, you send a wave, the air molecule will compress here and they are expanding here, right? And this compressed here. So it's just um, pressurized one area and decompressing another area. So the molecule is vibrating back and forth, the energy moving forward again. So that would be again a longitudinal wave examples. Versus the transfer waves, and if you apply a force upward into the string or rope, these are going up and down, and the movement of the wave is forward. So this is going to be a longitudinal. I'm going to show you a video after this lesson. So show you the longitudinal and um, transfer waves. Now, sounds versus light. Sound required a medium to travel, right? Without a medium, you cannot speak. Light doesn't. And how do I know? Just imagine the sun and earth. There is empty space between the sun and the earth, right? So, but the light travel from the sun to the earth means it doesn't need really a medium. And also, you cannot speak in a space. You go to a space unless that you can survive without breathing. So you cannot speak because to speak, you need um, air molecule to vibrate and travel through some medium. Now, sound transfer particles to particles and therefore would be non-existent in vacuum. This is caused because the source creates a change in air pressure, which continues onward in a direction. So that would be the example I just earlier explained. You have a string and you're just trying to vibrate it at one end, so the wave travel from one end to another end. We'll see that transmission of a sound through dense area is compression. Some part will be compressed. And rarefaction is transmission of sound through less dense area. So when you speak, it puts pressure on some area and expand another area, right? The one that are very close to each other or very intense is very dense. We call it compression, and the part that are very apart each other or less dense, we call it rarefaction. Again, the molecule vibrating back and forth, and wave or energy move forward. So they are along each other. So this is a longitudinal example. The speed and the medium. The speed of sound is faster in a stiffer material. Like if you knock a wood compared to um, kind of, if you want to see that, is the sound wave travel through wood faster or it travel through air faster? Of course, through wood. And the reason is that the molecule of the wood are much more closer to each other, so they can transfer the this energy faster, right? So they bump to each other very fast and transfer that one. But the air molecule, kind of they are really apart from each other. So for them to transfer waves take longer. They have to come and bump to each other, then transfer the. So more denser, it means more efficient. You can transfer that wave. And if you just remember those movies, like Western movies, if a person want to just know if this train is coming or not, so they don't put their ears through the air, right? They try to put their ears through this rails that is iron, right? They just put their ears there and they listen to the railroad, right? Because the railroad is solid, so transfer that wave sound faster. And they can really hear the sound of the wave, right? Because the solid transfer the sound wave more efficiently. So they put their ear on a railroad to um to know that if this train is coming or not. So, and is that the reason? Again, I'm going to repeat that. The reason is the particle are closer together in solid, allowing transfer of the sound from the source to be almost immediate, fast, and more efficiently. They transfer those energies. Any question? Now, the speed and the medium, these are the speed of sound wave in different medium at 0 degrees. So on hydrogen, very fast, right? Helium is 0 degree, again, very fast. 20-degree air is 343. At 0 degree is 331. Wow. So it seems if you want to compare the cold air and hot air, which one the sound will travel faster? The hot one. Okay. And the reason is that the hot air is more energetic. So they transfer the wave sound faster. So they bump into each other much more faster. So they travel. But the cold air, they just vibrating. They don't like their movement is not that a lot. That's why it's slower for them to transfer the wave. Okay, if give you a question in your request, say, is the hot air transfer wave faster or cold air? You say hot air, okay? If you want to compare gases and solid, of course, the solid will transfer the wave faster. See that? Compare the solid to just. So the denser is traveling, the sound wave gonna travel faster. Of course, the liquid compared to gases, so liquid transfers faster, and so on. Okay, very interested. The diamond. Look at diamond is 12,000 meter per second. That's really fast. Yeah. All right. Any question? So we're done. Success criteria. Now you can define different components of wave, calculate the speed of and frequency of wave, discuss how sound propagate and the factors that affect the speed. We did talk about the different states. We did talk about the temperature,